Okay guys, let's continue. I'm going to be moving forward with that of the transposes and the powers of the matrices. So let's try to look into the transpose of a matrix. It's actually an easy thing to do. I'm going to be citing example number 5 for this one. So given here a matrix, this is a 2 by 3 matrix, okay? We're going to perform the transpose of this matrix. So 1, 2, 3, 4, 5, 6. So this is actually your solution. So what did we do? We actually just inverted, okay? The columns of the matrix becomes the row, and the row becomes the columns. As you can see here, row 1, 2, 3 became column 1, 2, 3. Row 4, 5, 6 became column 4, 5, 6. So it's a matter of inverting the rows and the columns. I hope you got that. Okay, it's very simple. Moving on, we have here, we're going to be encountering a new kind of matrix. This is called the 0, 1 matrix. So it's actually often used in discrete structures. So why is it called 0, 1 matrix? It because its entries are either 0 or 1. It doesn't make use of any numbers. So it's as if we're dealing with binary numbers when you're using a 0, 1 matrix. An example of which can be seen here. As you can see, example number 7. Okay. So actually, there are some 0, 1 matrix that looks like this one. Okay. Again, they are just filled with somewhat a representation of binary numbers. Now, there are operations that we can use on 0, 1 matrices. Okay, we have here, we're going to find out the join of a 0, 1 matrix and the meet of a 0, 1 matrix, details of which are in definition 8. But I'm going to be proceeding with the solution already. On example 7, I have two matrices. Okay, and here same rules apply. uh, as you can see, if we're going to be finding the join of a matrix, it requires the join and meet. Actually, it requires that they have equal sizes. In this case, both of them are 2 by 3 matrices. So let's see, how do you find the join of a matrix? The join of a matrix is actually found just by, again, using a very familiar operation, right? So we are actually using here the OR operator. Okay, I hope you still remember, or we're going to be having a refresher in a little while on how to solve this one, okay, using the OR bit operations. Let us see that right now. Okay, so for the OR operator, if you still remember this table, the table for the bits operator OR and AND, we're not going to be using an XOR. If you still remember, okay, if we're dealing with OR, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 and 1 is 1. So same applies, same thing applies to what we're solving right now. Okay, so you just perform the OR operation, and there you go. You arrive with this particular answer. The meet, however, will be making use of another operator. Instead of the OR, we're going to be using the AND. You just have to consult the same table as what I presented earlier, and there you go. You are able to find the join. Join is associated with the OR, and the meet is associated with the AND. So it's a very easy operation to follow. Okay. Now we define the Boolean product of two matrices. So this is comparable now to the matrix multiplication, an activity I gave you earlier. So how are you going to be doing this? So actually, it's quite simple. This exercise, or this particular example, will definitely give you an idea of how to solve the matrix multiplication problem I presented earlier. Just a hint, so as you could use it. Okay, let's try looking into the example. I have here again two given matrices. The first one is a 3 by 2 matrix, and the second one is a 2 by 3 matrix. So Pertaining to the rules again, what do we need to do? We again need to find out if they are defined, and from the looks of it, they are. They're actually defined. So we should be able to end up with a 3 by 3 matrix just like this one. So to demonstrate how this works, I just copied, I hope you could see this one. I just copied the same problem. So how are we going to be arriving at this particular example or this part of the solution? So it's actually an easy thing to do. Let us try to locate where these parts have been distributed over here. So let me begin with that of the 101. Okay, where was that distributed here? They're actually here. That's 101. Where else? It's actually here and here. Okay, they are on those parts of the solution. And now, how will I find, how about the 010? Where could I find them? The 010 are actually here. There you go. And here at this part, and they're actually here. Okay, so you almost would want to copy the solution just by doing that. So now, where will I be able to find the 10? Okay, the 10 over here can actually be found here. These are all the ones, and these are all the zeros. So that's the 10. Where could I find now the 11? The 11 is actually on this part. Okay, that's the 1, and this is the 1. Okay, and finding the last part is the 01. This one again is actually here. All the zeros are here, and the ones are there. So you just proceed with the Boolean operations, and you will be ending up with that of a 3 by 3 matrix. Okay, I hope you got that part. Let's try to look into the next one. Okay, so we're done with the Boolean product. By the way, the Boolean product is determined by this particular symbol. Okay, so I am going to have the last part of the discussion here, and we're going to be looking into the powers of the matrix. As you can see here, we have example number 9, a 3 by 3 matrix. So we are going to find the powers of the matrix. So what if A has been raised to the second power? All you need to apply is the Boolean product. So A to the second power is equivalent to the Boolean product of A and A. So in that case, we just need to determine the solution. And then as you can see, A raised to the third power is just actually like A to the second Boolean product with that of A, and just find the solution. So it's quite easy for you to understand, I hope. And that's it. I'm going to be giving you some exercises, and I hope you understood or you learned something from this video.